because there are other codes which do similar things. There's a good reason we don't use those. So people always ask, why is it called binary C? Well, it's written in C, and it involves binary stars. And I know that sounds obvious, but it's probably the only code that's written in C that involves binary stars. There's one other in C++, which is a bit slower because it's in C++. But
I don't know if it's that much slower.
Yeah, it used to be. When I started this, it was year 2000, and in those days, C++ ran about 20% slower. So that's why.
So 20 years later.
It still runs a little slower, but it's not much. It doesn't really matter. But C is one of the languages. The good thing about C, if you know any other language, you can probably write in C. It's not that difficult. And also, it makes you employable at the end of it, because if you can write in C, you can write in any other language. So that's, I wouldn't suggest COBOL. That gets you a lot of money if you work for a bank, but other than that, I think C++ is very similar. You could work in Java or Perl or Python or things like that. I mean, the ideas are essentially the same. Python's a little different, but it's not hugely different. It's pretty much the same. So C is pretty standard, and it's something that a lot of people learn or learn something similar at university, so it's quite good. And I just despise Fortran. So it's not that Fortran is a bad language. Before any Fortran people on here, like Andrea, I guess you're probably old enough to use Fortran a lot. I am. And Geo, yes, sorry. So yeah, no, Fortran itself is absolutely fine. It's just the quality of Fortran that most academics write is absolutely terrible. And having used the Cambridge stars code for a long time, Peter Eggleton's code, it's written amazingly well, but it's totally unintelligible for normal human beings. So I decided to rewrite stuff with a slightly higher standard of modern coding than they had. And that is not to say that the code is perfect. It is not. There are parts of it which could always be improved, and I welcome any help anybody can give me in that regard. That's an ongoing task. But you can imagine binary C is a code that, as some people who are here today have said, they're using old versions. It continuously evolves. There are new things being implemented all the time. This last year has actually seen a lot of big improvements into the code, which I think will be very useful for a lot of people here. So it does keep improving, and it keeps getting better. And a lot of these ideas come from you. So I want to thank you for any ideas we have the next couple of days. Okay, so it's written in C, evolves binary stars. Why do we need a fast code? Well, you could use Mesa, for example, to calculate all your stellar evolution. People here do, some people do, I do occasionally. I use other codes as well. Other people on this list have their own stellar evolution codes. The problem is that stellar evolution codes are not that quick. You can't evolve a whole parameter space of stars. So let's have a look at what this parameter space is. I've got here a block which represents stars over a varying mass. So let's say you want to resolve a stellar population between 0.1 and 80 solar masses. Right? So that's, I can't see my mouse. Oh, there's a mouse. There we go. So you've got 0.1 on the left, got 80 on the right. And can we make this window disappear? Does anyone want this? Sorry, we've got a pop-up window. Hey, there we go. Perfect. Now let's say we fix the stellar physics. So we fix the metallicity, we fix the mixing length, we fix, I don't know, all the other stuff you want to do, like diffusion and all kinds of other stuff. And we fix the rotation rates to 0, say, for example, because that's the easiest to do. Might be right, but that's what we want to do. So we have a population, and let's say we want to resolve it. Well, probably you need about 100 stars in here. You probably also want to log space them, because that's how stellar evolution works. It changes more at the low end, so log spacing helps. But that's, imagine if you're doing that with Mesa, that's, you know, that's quite a bit of time. If each of your models takes an hour, that's 100 hours of CPU. I say an hour, that's assuming you don't want to do the AGB. If you want to do the AGB, it takes a lot longer than that, because you need to resolve these models properly. And sometimes it takes days, possibly even weeks. And if you're doing, say, an 8 or a 10 solar mass AGB star, depending on how you set the physics, that you could actually take possibly months of CPU just to evolve that until it dies. They're really tough to do. Now, that of course means that if you want to do stellar population studies, you're stuck. Even if you fling that at a big cluster, you're still waiting months for your slowest star to go. So that's pretty hard to do. And of course, you have other uncertain parameters. I've listed a few parameters here. There are many things in stellar evolution we don't know very well, right? So I've got here convection. I don't know if anyone here has worked on convection, but you have different amounts of overshooting, even undershooting. I'm not really sure how convection works in detail. Mixing length theory is all well and good, does some things very well, does some other things very badly. Mass loss rates are another thing. AGB and massive stars, there's a lot of issues there. A lot of people work on mass loss rates. That's not good.
I was upgraded, right?
You were upgraded to Pro. We have an issue with the Zoom link. We'll try to fix that if we can. Otherwise, we'll be thrown off in 10 minutes, and I'll send you all a new link. But that's fine. There's extra mixing in stars as well. I was at a talk just last week in China where people accreted material onto a companion star and didn't mix it. I'm not sure this is physically realistic. There's this thing called thermohalide mixing, which we know occurs. So why they ignored it, I don't know, but they did. There's stellar diffusion, which is something that's not in our models at the moment, but there's all these different kinds of mixing. So there's all this stuff. Rotational mixing, this is something that's become more interesting for massive star people in the last few years. I still don't know if there's any proof it exists. As far as I know, there isn't. Not really solid proof. So that's another thing to test. Magnetic fields. Anyone believe in magnetic fields? Some people here might. I'm not sure. And explosions as well. There's all kinds of explosion mechanisms. I've listed some here, but there are others as well, novae and stuff like that. So it could be a problem. Hello, Jonathan. Good to see you. It's turned up. It's nice. Some PhD exams. Who needs PhD? So here's a sort of example parameter space with a very simple stellar model. So we've got our stellar models going from 0.1 to 100 solar masses. Let's divide that into blocks. Okay. What we want to do is to set in each of these blocks a mass, which is representative of the block. Now this is a very, very low resolution grid. But it's not that different to the grids that were around 20 years ago when I started my PhD. This is the kind of resolution they had, if this. Maybe they had one massive star and that was about it. So they might do it in a log scale and you have a 20 and a 50 or something. Because stellar models were hard to make. Now you need a model to map this to an observable. So in this case, what I've done is take the luminosity as some function of the mass, and my model is really, this is my stellar model, this formula here. Clearly it's wrong because it doesn't work for the sun, but it's not bad for stars between 5 and 100 solar masses. It's okay. So you can predict the log of luminosity from the mass in this case, and that's a very fast stellar model. Now, where I got this function from, of course, I got this from detailed stellar models. But once you've got the function, you don't need the detailed stellar models anymore. You can just use the function to compute your luminosities. And I can calculate statistics. So I've got a mean luminosity of stars of 10 to the 4.9, according to this model. Not quite a very good model of a stellar population, but we'll neglect that for now. And a dispersion as well, which is this here. Now, all I've done is add these up, assuming they're all equal, which is probably not quite a good model. So here's our distribution, number of stars according to these blocks as a function of luminosity. And here's your luminosity peak. Very simple model, very wrong model, but that's fine. That's okay. We can compute this trivially in a few milliseconds less. Now, the issue comes then when we look at binary physics, because in binary stars, the parameter space is a lot bigger. And if you compare the size of this cuboid to the previous one, you have 3 main parameters in binaries, not just the primary mass, you have the secondary mass. You also have the separation, or alternatively the period, because they use Kepler's law to convert from one to the other. And this gives you a cuboid rather than just a long thing that you need. And so if you want 100 points in each dimension, you've now got 1,000,000. And you can imagine, if you have Mesa running an hour each, 1,000,000 of these is a lot of CPU. And then you get to the end and you realize you haven't done the AGB, and that's quite important if you want to make some kinds of stars. And you probably haven't done something quite correct, so you have to go back and run it again, and very quickly you use up all of your budget on Dirac or whatever your cluster of choice is. So this is a problem. It could also be a much bigger dimensional parameter space than this. What if you change the eccentricities? That's another dimension. I've ignored that. I've pretended they're all circular orbits, which kind of all right, but sometimes not. What if you want to change other things in your stellar physics? You have a distribution of initial rotations, or you have a distribution of metallicities, or things like this. So for stellar populations, it gets even more complicated, and you have a parameter space problem. So that's why we need a fast code to evolve these things, and that's where binary C comes in. Yeah, so this just illustrates the computing time problem. There's another issue I didn't mention, which is this factor 2 here. Binary stars take twice as long to evolve roughly as single stars, because you've got 2 stars. It's not surprising. So it becomes very, very expensive. And this was my old laptop. It's not doing so well. IT support said to me they're not supporting this anymore, which is a shame. But okay. Also, I've said n is 100. N might actually be a lot larger than 100. If you're looking at rare channels, and you don't know in the parameter space where they come from, so you can't put any a priori zoom on your parameter space, then your n may be actually quite a lot larger than 100. You can mitigate this somewhat, and we'll talk a bit this afternoon about the binary grid code that I use to do this. You can choose where you put your stars in the parameter space to make it as efficient as possible. That is something we can do. For example, if you want time resolution, so you want so many stars per mega year, then you can choose the masses so that your stars evolve at exactly the times you want. And you can resolve it much better that way. You can also work in log time, which makes it faster, and I'll show you some examples later. So how was this done originally? So in the 1990s, there was a series of papers based on the Eggleton-Fitchett-Tout paper of '89. These finished eventually in Jared Hurley's PhD, which is a very good read. So if you ever want to learn about stellar physics, actually, it's a very good introduction. So he had 2 papers in 2000, 2002. 2000 is the SSE code, single star evolution. 2002 is the BSE code, which is not mad cow disease, for those who know about BSE. That may have been a deliberate pun, I'm not sure. If you've met Peter Eggleton, you know it is. But the 2002 paper is the one that has all the binary physics put into it. And I should say this paper is really key for us because that's what the main physics in binary C comes from. It's also, if you use Maser binary, it's the same physics in that, essentially. There's very little difference between the two, which tells you that Maser really is not that good at doing binaries yet. And that's because they're hard. The reason that Maser struggles is because it's computationally difficult to do binaries. One thing I didn't mention when I was talking about the timescales for each model run, I just doubled it for binaries. It's actually, of course, a lot longer because as soon as you have mass transfer, your timescale for your length of time you need for CPUs is enormous. You need tiny, tiny time steps to do mass transfer properly. So having a fast code is one of the advantages, is also we can do that a lot faster as well. Now, all the models that are in binary C are based on these SSE and BSE models. They are from the Pols et al. Set of models from 1995. So Onno Pols made those. They're pretty old now, but I think the stellar physics is probably fine. I mean, it was as accurate, and it was calibrated then to clusters, so you get the overshooting correct and stuff like that. So the ages were fine. This is one of the things that Geo is trying to upgrade in our models, trying to change it so we can put in any model grid we want. But at the moment, we have a set of formulae based on the Pols et al. Models. Now, binary C was originally forked from BSE in around 2000, 2001. This is what I did during my PhD. And I told you I hated Fortran, and BSE is one chunk of 10,000 lines of Fortran, which is not the best way to run a software project. It's very fast because it's one chunk of Fortran, but it's also rather hard to include new things. A lot of it is copy-pasted code. So you have 2 chunks of code, one for stars that aren't undergoing Rush-Lobe overflow and one for stars that are. What's the difference? I don't know. They're just slightly changed, but why you should copy-paste that, I don't know. So the code itself is actually very hard to update and to put new stuff in. It's not impossible, of course, but it's hard. Now, at the moment, we're still mostly using their stellar evolution, but there have been a lot of updates, particularly to the nuclear synthesis, which is what I put in during my PhD and afterwards. And we'll go through those in a few minutes. So just to give you an idea of what Onno Pols grid does, it's limited in metallicity. There should be an extra 0 in the metallicities there. Sorry about that. So it goes 10 to the -4 up to 0.03. So the low metallicity at the time was probably lower than any star that had been discovered at that point. So that's why they did it. And the upper limit was probably the opacity tables. I'm sure they didn't go any higher at the time. And indeed, that may still be a problem in certain cases. The fits are in the Eggleton, Fitchett, and Tout paper. That's the zero-age main sequence fits. And the Hurley paper includes, the 2001 includes stellar evolution all the way up to the end of the AGB and white dwarfs and everything. These are using Peter Eggleton's stars code. Those of you that don't know it, you can download it from the Cambridge. These are all based on Eggleton's old stars code. I don't know if you heard that bit. And a limited metallicity range, but that's okay. I mean, the metallicity range, 10 to the -4 to 1.5 solar at the time, that's not bad. That's pretty good. Now, the way that the stellar evolution code in SSE, BSE, and binary C works is you divide the stellar evolution into various phases. Now, we're all familiar with many of these, such as the main sequence, the Hertzsprung gap, giant branch. There's nothing unusual, I think, about this. There is also the stripped phases, which don't exist in most single stars. So, for example, low mass helium stars, which you don't get other than through binary interaction. Ono also made a set of models of helium stars, which are in SSE and BSE. He never published them. You can ask Ono why, somebody can, but he never published it. He never got around to it. He was doing other things. But these sets of models are actually available. If you want to download these models, then you can get the detailed models. I do have them somewhere. I'm happy to share them with people. I think Chris Tout has a copy on a CD-ROM somewhere. So, you know, I'm not sure the younger people here have ever heard of CDs.
Ages.
Like a wax cylinder or something, punch card type thing. But these models do exist. What they did was to divide each phase of evolution into a start point and an end point. A lot of this was done by eye in a Hertzsprung-Russell diagram. You look for where the curves wiggle around in the appropriate place. It's not so easy to do this in an algorithmic way, but by eye is very easy. There are also simple models of white dwarfs. There are several different options for white dwarf cooling tracks, which are in there. This is something I think could be improved a lot. It's never really been an important point for us, but if you want to look at exact positions of white dwarfs in a color magnitude diagram, this is something that really needs working on. Neutron stars and black holes are in there as well. We treat them as point masses, essentially like everything else. There's nothing particularly thrilling about them, except that they have very small radii and high masses, essentially it. And we can, for black holes, you just use the Schwarzschild radius. You could put in more physics if you want, but it generally probably doesn't matter. So that's how we divide those things. I'll give you an example of how we do this. So this is a set of zero-age main sequence models I made that I then evolved for a bit. These are detailed models. Okay, so I made these using Twin, which is an updated version of the stars code. It's just that we have a graphical interface for that. So it's very easy for me to make grids. What I've circled here is the zero-age main sequence. I think you all know what the zero-age main sequence is, where the stars start burning. You can then use a fit like this. This is from the Eggleton-Fitchett-Tout paper. It was used in the Hurley code. They're complicated formulae for the luminosity as a function of mass and the radius as a function of mass. Now, I think this is from the original Eggleton-Fitchett-Tout paper, so there's no metallicity dependence in this, but it's for solar metallicity. It's already quite complicated. Well, it looks complicated to you. To a computer, this is easy. Of course, it doesn't care. You can very quickly calculate it. It's very fast. And so the fast code in the end, it turns out to be at least 1 million times faster than the detailed code, just to calculate the next. And the fitting formula still, even with state-of-the-art models, looks pretty damn good. Okay, so that's all the way up to 150. The fitting formula itself probably actually should only work up to around here, somewhere. Somewhere up here is the edge of the model, but it extrapolates extremely well. And that's just luck, of course. That's fine. But it still works very well, despite the fact that these new models have different physics, got upgraded opacity tables and things like that. It still works pretty well. And this is why I think using these formulae is not such a bad approximation even to what Maser will give you, because it will give you essentially the same zero-age main sequence for this set of, say, mixing length and stuff like that, which of course does change. So each phase of evolution has a lifetime associated with it. For example, the main sequence, you can use a formula like this to calculate what the lifetime is. And then inside the code, normally these lifetimes are normalized to be between 0 and 1. So you have start of the main sequence and end of the main sequence, and you have the time in between. And then you can calculate the luminosity and the radius here as functions of not just the initial luminosity and radius, but with these correction terms based on the time. So as the star evolves through the main sequence, it gets brighter, for example, it gets a little bit redder. So that's kind of what you expect, very quick to do. And these constants, alpha and beta and gamma here, and alpha prime, beta prime, gamma prime, they're all functions of mass and metallicity in the code. So you can do everything for different metallicities. To give you an idea of what they look like, this is kind of what they look like in the code, just for solar metallicity. But again, the computer doesn't care, it's complicated, but all these parameters were done by Jared in his 2002 paper or his dissertation. They're the same, essentially. And all these are in binary C, so they're all calculated for you. On the giant branch, things are a little bit different. You don't have such a simple fitting formula, but you can fit the luminosity to be a function of the core mass on the giant branch. It's a very, very tight relationship. There's a little bit of dependence on the total mass, but it's mostly the core mass. So you end up with this first expression for the luminosity. You can relate the core mass growth rate to the luminosity, of course, because the luminosity is causing the core to grow. They're related. So you can calculate the rate of core growth as a function of the core mass. So given a starting core, you can work your way all the way up the giant branch. You know the luminosity, the radius is just a function of the luminosity as well. So a function of the core mass, depending on how you want to write it. So it's actually quite simple to go up the red giant branch. It's quite simple to go up the AGB with very similar formulae. The AGB is a little more complicated because you have third dredge up as well, which then decreases your core mass, but that's all in the code, so it's fine. So yeah, so your giant branches are pretty easy to do, also very quick. A giant branch, of course, is easy in stellar evolution. It's just a line up the HR diagram, so it's actually quite easy to test. And so you end up with models that look like this. You can guess which one are the detailed models. Of course, they're the ones on the left, because they have a few more wiggles in them, and the ones on the right are the very fast code, runs 1,000,000 times faster, but gives you almost exactly the same. Okay. So a lot of the things are still there. The little hooks at the end of the main sequence are there. The giant branches are in the right place. The main sequence looks almost exactly the same as to the giant branches, so it's pretty good. Note that in many cases, the stellar evolution ends on the giant branch when you're computing these kind of models because there's convergence issues. We don't have that problem in binary C. You can keep going with the core mass as far as you like. Now, of course, you're extrapolating a bit doing that, but it's generally not too bad to do. This is particularly a problem on the AGB. Many AGB models just crash because of various either numerical or physical instabilities that may or may not be real. This is something that is still being discussed in the literature. I read a paper about that just last week. So with binary C, you have the option to keep going. It's a lot more numerically stable in that regard, which is a good thing. Okay, so that's essentially the physics that's in there, or at least was in there at the beginning and is the main bulk of the code. Now, I want to tell you a bit about the support that you have for binary C. This is one aspect of binary C that the other codes generally don't have, is that there's quite a big user group that actually are using it. You can get help from anyone at any time. There's documentation, which is in the code. It's also online at this link here on my website. I've managed to get it converted from the PDF, so it looked quite nice. So I try to keep that up to date. It's not to say it will be, because it's quite big. Of course, there's a lot of stuff in there. There's a whole section on how to install. There's a whole section on how to run it, and there's also more detailed descriptions in there. It's not all detailed. Some of it is quite introductory. It depends on how far you want to go. There's also a cookbook at the end, so you can look if there's something you actually want to do that's a specific special case. There's a few of those in there, so you can then look and see how to do it on there. The code itself is on the Surrey GitLab server. I'm sure you've all tried to use this now. It was down a bit at the weekend. I have no idea why. It seems to be okay now. It generally works very well, actually. It's very reliable. Once you've got a login. Now, please don't ask me why our IT services require you to have a Gmail account to log in. I don't know. That's, yeah. Why it has to go to them to be done, I don't know either. But today, for example, we got someone, I forget who it was, someone this morning it took about an hour for them to get permission. So they're actually pretty quick these days. It's not too bad. But all the code updates will go in there. So you can use everything you're familiar with Git. So if you ever want to update, you just go to the master branch and you do a Git pull and you'll get the latest. What's that hand waving from David Hughes?
Master branch is like bleeding edge.
Yes,
To
absolutely.
do a real release.
That's right. There are real releases. So the latest was 2.15,
It's better as well.
which you can get as well. Fixes will go into master, and every so often I will tell you when fixes get released because I've tested them. So. But you can also report bugs on there. There's the automatic GitLab bug reporting thing, so please do. That's fine. I've put a few for myself there as well, and I've allocated some to a couple of people here. So whether they'll get fixed is another question, but you can harass me, that's fine. There's also a wiki on there, so if you want to start a wiki page to talk about something, you can also do that. So we have a wiki page for this meeting. So all of your email addresses are on there, but that's private. Nobody else from outside can see it. So that's the idea. We also have mailing lists. There's the development and announcement mailing lists. You can sign up for those if you haven't already. There's a Facebook page, and we also are on Twitter these days. It's very modern, isn't it? Someone remind me of what David Cameron said about Twitter. What was it? Too many tweets make a twat, I think it was. So that would be me on Twitter. So, you know, it's the only funny thing he ever said. You can also email me, and this is what most people do when they have a problem. They just email me, and I try my best to fix it on a Sunday night when I'm very jet lagged like now. So that's okay. I don't mind doing that. That's all right. If I've got time, I'll do it. If I don't have time, I'll let you know. That's often the case. If I'm teaching or looking after family or stuff. That's how it is. Okay. Oh, that's the end. That's the end of the introduction. Do we have any questions from anyone? I mean, you can interrupt at any time, I should say. Hello, world.
Just a couple of slides earlier, does binary C get the length of time stars spend on a blue loop post-being sequence, right?
Well, the blue loop will depend on your input physics quite sensitively. And I believe in the Pols et al. Paper in '95, when they constructed the models, they tried to fit the blue loop to observations. So they fitted the overshooting to the observation. So it should get that right. But whether it's accurate enough for what you want to do is another question. If you think this is something we should focus on in the model grids that Geo is developing now, you can talk to Geo about it over lunch. That would be a good time to talk about that. Any other questions?
Rob, I'm not sure if you're going to talk about it after, but in the question of what are the difference compared to other population cities code, you're going to talk about this after? Like compared to BSC itself, compared to other popular ones that exist right now, like Star Trek Compass, etc. If there are, like, what is the sharp answer of, like, what are the main differences? They all use same.
Sure. No, in some ways that's true. So Star Trek is a rewrite of BSE in C++. It focuses on massive stars. They don't do anything in low mass stars, not really. And we have nuclear synthesis, which I'll talk about in a minute after this. So we also have some physics updates, which they don't have. I'll give you an example. We had a conference on binaries in Cambridge, was it 2 years ago, I think it was? I'm not anyone here. 3 years ago? Time flies. They showed a wonderful image of main sequence lifetimes as a function of mass. And they had 3 curves in black. One was BSE, one was, I think, Saber, which is Portuguese Svarts code, and one was Star Trek. And then they had a curve in red to make it look very wrong, which was binary C. And it was quite different to these other 3 codes. And these other 3 codes are all based on the same original physics, except that binary C has its main sequence lifetimes for massive stars, anything over about 20, updated so that you're not extrapolating the fit anymore. It's actually using a table, which is from Norbert Langer's code, I think, a grid of models one of his students made. So our physics was updated so that it was correct. All of theirs was wrong and extrapolated, but they presented it in a way that binary C was wrong, and clearly the red one is always bad. And I had to make the point, I'm sorry, ours is right and yours is wrong. And that's just, it's not my fault, you're just extrapolating. And so you've got to be careful when you extrapolate over about 50 solar masses, because everything in BSE, and hence everything in Star Trek as well, and in Saber and in all the others, is going to be an extrapolation. When you see papers by people who are making models of globular clusters with 300 solar mass stars, and there are people that use, for example, the N-body code from Sverre Aarseth, he uses the BSE code underneath to do all the stellar evolution. But they have all these mergers inside the globular cluster. They get up to 300 solar masses. Everything they're doing at that point is a guess. Okay, it's not to say that their fitting formulae are completely wrong. Well, it is, because actually you get a nan if you do it properly, but you know, that's how it is. And they publish papers on this, and nobody quizzes them on it. I don't think you should do that, because it's just wrong. It's not proven to be correct. And you know, I set higher standards than that. So that's one of the reasons actually that I think the work that Gio is doing is very, very important, because he'll be upgrading the stellar physics to use pretty much any mass between 0.1 and hopefully up to 1,000. It's not to say 1,000 mass solar mass stars actually exist or for very long, but in a cluster you might make it happen. So we have plans to do that, and I think the compass code doesn't really do stellar evolution properly, if I understand right. Or at least the mass transfer is a sort of black box, where you put in your values and you get values out. It's very similar to the original Brussels code. The guys in Brussels, this is the Dutch-speaking guys in Brussels, Dutchish-speaking guys in Brussels. They had a code based on this is Van Beveren and Nicky Mannekens, I think it's the newest guy working on it. And they're very nice people, and they have a code which, again, it's to do mass transfer. What they do is they say, you start mass transfer with N1, N2 in a certain period, and here's an algorithm that gives you, it's a black box, gives you what you get at the end. In binary C, we actually do the mass transfer properly. We sit there and we calculate at each time step the mass transfer rate, so that you can then calculate how many stars you should observe in this mass transferring phase. And I think that's also very important for what people here want to do. So we don't really have this black box. And indeed, if you look at their papers, you see some tracks in the Hertzsprung-Russell diagram which go into a box and then come out the other side. You've no idea what's happening in that box. I tried to read their papers, but it's like 200 pages of very complicated stuff. So it's quite hard to do. So I think where ours differs is we have upgraded the physics where we can. We put in the nuclear synthesis as well. Now, I mean, the Brussels code also has some nuclear synthesis, so it's not, we're not the only people that do that. But I think we do it a little better in that we treat the mass transfer a lot better, which means we can also do wind mass transfer objects like barium stars, CH stars, carbon enhanced metal poor stars, which they can't do so easily. So that was a bit long. I'm sorry. Does that answer the question? I don't know.
Yes.
Manos has gone to sleep. I'm sorry.
No. Pretty much, I've got this question pretty much. So usually that's the two main things I have been mentioning, and I wanted to see if I'm forgetting something. One is the nucleosynthesis, and for massive stars, the new feeds that Fabian Snyder that you mentioned in the lifetimes.
Yeah, so we have a load of other upgraded stuff. I mean, the nucleosynthesis comes with proper AGB models from Amanda Caracas from, those are back from 2002, I think, but they are proper detailed AGB models. Nobody else has those. So if you want to look at AGB physics, which is quite important, we're the only people that do that. All the others use very approximate AGB physics, which was in the BSE code, but bear in mind they don't actually have any thermal pulses. AGB stars have thermal pulses. We do those in detail in binary C. In the original SSE and BSE, they chose their time steps to be so long, they evolved straight through the thermal pulses, which gives you a rough idea of what the star's doing, but you don't get the core masses right. You don't get the luminosities right, you don't get the radii right, and you don't get any nucleosynthesis out of it because there's no third dredge up. So you don't ever make carbon stars, which we know exist. So in order to do the nucleosynthesis properly, our code actually does that. And indeed, the geometry of AGB stars is such you can do it pretty fast. So we have all the third dredge up of carbon and all the other S-process stuff, that's all in there. You can use the geometry of having a very big convective envelope and a tiny core you can use that to speed up your code. It's essentially one big block of very well mixed material, and you just need to fit what happens at the base. We also have a hot bottom burning code, which I've used to do some nucleosynthesis studies. That's kind of fun. So I'll talk about that in a bit. So I don't want to go into too much now. Anyone else got questions? Anyone here? Okay, so I'm going to go on to the next talk, which is part 2. Let's see if I can get this to work. My CPUs are going mental. I don't know what Zoom's doing. Maybe that's why it's good. So what was talk 2 about? I can tell I wrote this yesterday. Talk 2 is about the physics. Okay, that's kind of fun. Let's see if I can get Zoom to work. Come in, Zoom. select a window you'd like to share. This one. Great. Okay. So let's talk a bit about actually this may answer some of the questions that that people had. So